Hi, hello, my name is Ana Luisa. First of all, I would like to thank to the organizer for the opportunity to be here. This is a pleasure. Today I'm going to talk about constraining cosmological parameters using H2 galaxies. Here I show you the collaboration group. I would like to comment that this project started with Roberto Terlevich and also with Elena Terlevich and Jorge Melnit. But they have to wait more than 30 years for the instrumental development in large telescope to carry out this project. And here you can also see another phases in the collaboration. Like as a very quick review, the standard model of cosmic structure formation, or the lambda CDN model, explains the history of our universe as a succession of epochs characterized by their expansion rates. And the cosmological parameters for example, the matter density parameter, omega m, or the W parameter, which correlates the pressure with the mass energy density parameter, are obtained when we combine low redshift results given by supernova and baryonic acoustic oscillation with very, very high redshift results given by the CMB. In this plot, I show you the distance modulo difference when we include cosmological models with evolving dark energy. And here you can see that the maximum difference in the cosmological models that include the dark energy occurs at redshift higher than 1. And so in this sense, the aim of this project is to populate the holometric diagram using a single distance estimator to the highest redshift possible. Right now, thanks to the James Webb Space Telescope, we can constrain cosmological parameters using H2 galaxies up to redshift 13. And to do that, we have to use a correlation that we call it the L-sigma relation that correlates to the Balmer line luminosity with of the emission lines, typically H beta emission line, but you can use H alpha if you want, with its velocity dispersion. But what are H2 galaxies? H2 galaxies are very young outbreaks of star forming. Here I show you a H2 galaxy prototype. The name is 1Zwicky 18. And the physical properties that these targets have is that they are very compact. The size of these targets is around 1 kiloparsec. They have low metallicity, low masses, high star formation rates. They are very young, with age lower or younger than 5 megayears, and they have a very luminosity per unit mass. In this image, you can see a mosaic of H2 galaxies, and here you can see that we have Greenpeace galaxy, for example, and also we have the blueberry galaxies, but we can see that H2 galaxies have a rainbow in colors, and this is because we are not fitting the redshift. For example, Greenpeace galaxies are green because the oxygen 3 emission lines fall in the green filter on the Sloan, and so for this reason they look green, yeah. But if we didn't constrain for redshift, H2 galaxies have a lot of colors, and the color depends with the redshift. And how we select H2 galaxies? We select H2 galaxies by the equivalent widths, because stellar population models predicts that if we select targets with very high equivalent widths, typically higher than 200 in rest Armstrong, the bores, the star-forming bores, is younger than 5 megayears. Also, we know that H2 galaxies fall in the high ionization and low metallicity region on the VPT diagram. No, I don't have the laser. And when we observe H2 galaxies using very high spatial resolution, we can see that we have several clumps inside one galaxy. This means that H2 galaxies represent to the population with the Younger's system that can be studied in any detail. Also, by selection, there are the population of extragalactic system with the stronger and narrow emission line, typically with velocity dispersion less than 90 kilometers per second. Okay, so here I show you the Elsimer relation. The dark blue points here represent our uncle sample. This is giant extragalactic H2 regions that they have distance estimated using primary methods. For example, in this case, this H2 or this giant extragalactic H2 regions have Cepheid distance. The distance are estimated using Cepheids. The blue points represent our local sample. The higher redshift the blue points with the higher redshift is around 0.15. And the rest of the points, the colors that you can see there, is our intermediate redshift sample. Here I would like to comment that when I published that paper, I called them higher redshift galaxies, but right now I can say that. This is intermediate redshift. The higher redshift here is around 2.6. And something very, very important here is that the slope in the Elsimer relation is around 5, which means that this is more important that we estimate very well the full Will-Hat maximum of these emission lines because the slope is 5. And so we have to measure with a lot of precision the full Will-Hat maximum, even better than the fluxes. And so for the reason, we need to observe them using the highest or the biggest ground-based telescope that we have and with very high spectral resolution. For the reason, my advisor at that time waited a lot of time to do that. Here I show you how the spectra of these targets looks like. This is a very high spectral resolution that we can observe and a local H2 galaxies, for example, using Subaru. When we can see on the top panel the oxygens and the H beta, and in red, the line that you can see in red is the profile of the instrumental resolution. So here we can see that we are resolving the emission lines. On the bottom, the same, also our local sample, but using BLT, also with very high spectral resolution spectrograph. And the profile that we are observing, I show you in the bottom plots. The most of the targets in the local H2 galaxy sample have the profile is Gaussian. However, we can observe it also like winds in the profiles, and so for this reason, we're also performing multi-Gaussian fittings. And we believe that these winds are because on the H2 region we have OB stars, and so these stars eject material to the medium, and for the reason we have winds. Okay, but when we go to the intermediate redshift sample, here is the spectra that we are observing on the top panel with BLT, CMOS, and we can see the oxygens and also H beta emission line. And this is a target at redshift 2.2, and in the bottom panel is the same target but observed with MOSFER at Keck. And this is the profile that we are observing. This is a target at redshift 1.5. This is H alpha profile. And here you can see that the profile looks Gaussian, but of course we are an intermediate redshift, and so maybe we need more. We need more spectral resolution, but this is something that we can do with what we have. And also here I performing a Monte Carlo analysis to analyze the uncertainties in the velocity dispersions. And so how we constrain cosmological parameters, I'm going to focus more on the results, but essentially we compare an observed distance modulus, which depend of the floods and the emission of these targets, and also with the velocity dispersion that we are measuring, and with the slope and the 0 point in the L-sigma relation. And we compare that distance modulus, that observed distance modulus, with a theoretical distance modulus, which depend of the redshift and on a set of cosmological parameters, and of course, of our uncertainties. And so when we just constrain the matter density parameter, the results that we obtain are shown in blue in that plot. And if we compare with another distance estimator, for example, with supernovae, our results are in agreement inside 1 sigma, but here I have to comment that our uncertainties are larger, but maybe it's because we are using a sample less than 200 H2 galaxies, when the most of these H2 galaxies have a low redshift. And for example, if I come back to the past and compare with the results that supernovae have using more or less the same redshift run and more or less the same sample, the amount of targets, our results are in very good agreement with those given by Torrey and collaborators using a sample of similar size. And when we constrain the omega M and W space, just using H2 galaxies, our results are shown in the middle panel in red. And when we compare with the results given by supernovae on the right panel, we also can see that our results are in very good agreement are in agreement inside 1 sigma with supernovae. And when we perform a joint analysis with CMB and BAOS, our results are shown in that plot. Okay, here is just for comparison with doing the H2 galaxy CMB and BAOS in red, in black for the WCDN model, and supernova CMB and BAOS in red, and on the right panel, the same, but using the CPL modem. And here I show you that, of course, we have larger uncertainties, but we have to note the huge difference in the amount of targets that we have, less than 200 versus more than that 1,000. Is it possible to constrain cosmological parameters, including high redshift H2 galaxies, just using local H2 galaxies? And if you are interested, you can go to this book. But just to show you that, yes, this is possible, and our results are also in agreement, but we have large uncertainties in comparison with another methodologies. But at least for me, the most important of this talk is regarding the systematics, because I have to say that we have a lot of problems that I would like to analyze. For example, if we come back to the L-sigma relation, we can see that the scatter on this correlation is larger than the intrinsic uncertainties associated to each target, which means that we have a second parameter that we have to analyze. This is something that we have done for our local sample. We have analyzed the systematics, but I'm not going to talk about that because my work is more in high redshift sense. But yes, we have a very good idea what are the systematics that we have, and in this paper, Chavez and collaborators 2016, we estimate a systematic error budget in the distance modulus. And so we know that the most important systematics that we have is, number one, is the size of the bores that have a large error budget, and also the extinction. And so let me go back to the previous image that I showed you, that inside one H2 galaxy we have several clumps, and so each clump follow the L-sigma relation. But when we go to high redshift, it is not possible that we can resolve a spatial resolution. We can see that clumps. And so this is a very important systematic that we have. We are measuring the size using James Webb Space Telescope, but we have to understand that right now it is not possible to measure the size for each clump inside one H2 galaxy. Another very important point is in the bottom panel, you can see several extinction curves. And what is the best extinction curve that we have to use? At the beginning, we were using Calcetti extinction curves, but then we realized that this curve is very far away from another extinction curves. For example, for the Gordon extinction curve, and this Gordon extinction curve is based on a giant extragalactic H2 region prototype that this is 30 Doradus in LMC. And when we compare that extinction law with high redshift extinction curves, the extinction curve are neither that with the Calcetti. So for this reason, we changed to that extinction curve. But we can constrain cosmological parameters using whatever extinction curve that you have. But of course, I would like to know what is the best extinction curve that we can do. And also here I show you the Hubble volumetric diagram for H2 galaxies. In the bottom panel, I don't know if you can see giant extragalactic H2 regions that when we have the distance estimated using Cepheids. In the middle panel for the local H2 galaxies, and the top panel for high redshift galaxies. And if we compare the scatter, for the high redshift galaxy, we have larger scatter for our local sample. And this is because in that time, when we request time in this big telescope, they just give us observational time using just one band. So we request for more observational time, and we get the data, and we have to do all this analysis in order to apply the Balmer decrement in order to get a better extinction for these targets. But this is something that we can do in a couple of months, and we hope that we can do that. What is better, increasing the sample or reducing the uncertainties? And so this is a simulation that one collaborator did a long time ago. When using supernovae, he reduced the uncertainties to the half, and so the results that he obtained are shown in red on the left panel. But when we increase the sample using the same redshift range, the results that we can obtain are shown on the right panel. And so here you can see that this is more important to increase the data that reduce our uncertainties. But of course, I would like to do both. And I think that this is something that we can do. And this is another simulation, but when we performing mock galaxies. And in that time, there was no James Webb Space Telescope observation, and we performed the mock simulation using the VLT, the redshift range that we can observe. And when we include 500 high redshift mock galaxies, the results that we observe are shown in gray. Okay, and so let's go to the high redshift. Now it is possible that we can see or resolve galaxy morphologies, even a redshift higher than 6. And this is amazing, because we can go to very different size or scales in these targets. When we can see, for example, emission lines, for example, oxygen 3 and H alpha to parsec scales. And when we go to see these amplified gravitationally galaxies, we can see individual clumps in that galaxies. That this is amazing, because we go to parsec scales a redshift higher than 6. And so this means that stellar systems showing strong emission lines dominate the light of their galaxies, suggesting that a star cluster might be a dominant star formation mode for young galaxies. This is exactly what happened with an H2 galaxy. And so this means that we are observing H2 galaxies at high redshift. And in this paper that was accepted a couple of weeks ago, we show for first time the Hubble telemetry diagram for H2 galaxies at redshift 7.5. The James Webb Space Telescope are shown in green. And also we increased the data that we can obtain with VLT and Keck telescope up to redshift 3.5. Is the maximum that we can do with ground-based telescope, observe up to redshift 3.5. This is not possible. If we want to go deeper, we have to move to James Webb Space Telescope. And this is the LCMA relation that we found for this sample. And this is the likelihood corresponding to 1 sigma and 2 sigma confidence levels when we have all the parameters free, the 0 point, the slope, the Hubble constant value, the omega m, and the W parameter. And our results with that uncertainties are in agreement with lambda CDM, but maybe in the future, when we increase the data and analyze a little bit more the systematic, maybe these results can change. We didn't know. And I started to work a little bit more in detail with James Webb Space Telescope, and I started to get inconsistent. For example, when I observe the same target, but when I use the spectra coming from the mass data archive and compare with, for example, with JADE survey, the spectra for the same target is different. And so for this reason, I start to do the photometry, and I see that when I perform the photometry using the slit in from the near spec on the James Webb Space Telescope, the photometry that I am obtaining is in agreement with the mass spectra. But when I correct for path loss, the photometry, the results that I obtained is in agreement with the JADES. And so this means, we wonder, is the path loss correction defined for point sources, and will it generally underestimate the correction for significantly extended sources? And the answer is yes. And so in this moment, I believe a little bit more with the JADES spectra, because at least they correct for path loss. But if you can use if you want to use the mass data, you can perform the photometry and correct that, and that's it. It's possible to do that. This is an example of an H2 galaxy observed with James Webb Space Telescope, when you can see H alpha and H beta in the oxygen lines. That's amazing, because the signal to noise is very high. And also, I download all the spectra, the high resolution spectra that is possible from the JADE survey, and I start to work with that sample. The highest redshift that I have available right now from the JADES survey, for example, this is in PRISM, a redshift. This is an H2 galaxy, or a candidate to H2 galaxy, a redshift 7.2, and this is, and on the right is the high resolution grating, and this is the profile that we can use to know what is the full Wilhelm maximum, and this is the higher redshift that I have from the JADES right now, when we can see the oxygen emission lines. And just to finish, I would like to comment that we start to collaborate with Jorge Zavala in order to use also ALMA synergies with James Webb Space Telescope. And here I show you the most distant astronomical object with direct spectroscopic detection of emission lines, H alpha and oxygen 3. In the top panel, you can see the 2D spectra. In the bottom panel, you can see the 1D spectra. When in the right panel, you can see the profiles of oxygen 3 and H alpha. And as a very, very preliminary, we just put that using our previous cosmology. And we see that this target follow the L-sigma relation. But we have to perform the fitting. But just put what we have, this new target. You can see that this target also as in agreement with the lambda CDM cosmology, but okay, this is something that we have to improve. And that's it. Thank you very much.
Thank you for your talk. I would like to ask if you checked how much the Redshift and the extinction law influences affect your result. I mean, if you choose an extinction law, then another extinction law, how much the coefficients will...
This is a work that I did a long time ago. Yes, the more or less like omega m in that time, like 5 years ago, it was around 0.24. And when I use another extinction law, it was around 0.25, more or less. It's not so much, maybe, but something that important is that the intrinsic scatter in the correlation also is lower. And so it's not just a matter of use one extinction law and another extinction law. This is a matter that we can also have, for example, the Balmer decrement, that this is something that this is not possible with the current observation. But now, thanks to the James Webb Space Telescope, I have H alpha and H beta emission line in the same wavelength range, more or less, and this is something that we are doing right now.
Hi, maybe it's technical, and maybe you said it and missed it, but when you talked about the path loss with the JWST, does that affect both the just the continuum that you observe, or also the shape of the...
No, just the continuum.
Okay.
It's because, it's just the fluxes. But this is because for standard sources, the slit width that we can observe with near spec is lower than the size of the target. And so you have to correct your fluxes for the size.
But you believe that the line shape wouldn't change because of that?
Yeah, because the full Wilhelm maximum, it depends of the size of the target.
Okay, thank you.
Well, thanks, Luisa, again.